Very warm welcome to this Open Neuromorphic community talk. We are very pleased today to be joined by Professor Christian Axenie, who is a professor, assistant professor of artificial intelligence from the Technical University of Nürnberg in Germany. He leads a research group there, but got his PhD from the Technical University of Munich under the same supervisor that I'm currently having, Jörg Conrad, as a fun fact. He has been working as a researcher in industry for Huawei, and he's garnered an impressive amount of experience, more than 15 years in academia and more than 7 years in the industry. I personally met Christian at the KTH Royal Institute of Technology, where he visited us, and I remember that visit fondly because he talked about some very exciting technology, including anti-fragile systems, which, as far as I understand, he was actually the one to bring into neuromorphic or neural systems. So, Christian, I'm very much looking forward to hearing your talk, and please take the stage.
Well, thank you so much, Jens, for a very nice introduction. Actually, we'll not talk today about anti-fragile control system, but we're actually going to look at some really interesting project that I've developed with my undergrads. It was actually for a TinyML challenge and took place between May and October last year. Basically, it's like type of hackathon. You have some really nice problems to solve. Then there are huge sponsors coming in and chipping in hardware. And guess what? My students were like, okay, let's do that. So here we are. After like some months of work, we got some really interesting results. And actually, it's an award-winning solution because we got second place. Important to mention is that there were like 29 teams and they were like mixed university and companies challenging against each other. Yeah. And now, stripping away all this fluff with the hackathon, I want to introduce you like the actual approach we've taken, which looks at hybrid learning. Hybrid learning because we looked at spiky neural networks on one side, and on the other side at traditional machine learning, which live together, coexistent on an embedded platform in order to make streets safer. So we looked at roadside safety, and basically we try to tackle visual motion detection and tracking of pedestrians. Interestingly enough, I'm after a long journey in the industry where I didn't do so much neuromorphic, but like way before that, I spent like at least 6 years. And I remember a couple Kacha and Telluride workshops where our neuromorphic colleagues back then, Sadiq and Dylan and some from SynSense, were like still having fun in Capocacha and hacking nights and days with robots and sensors, where neuromorphic was not that commercial, so to say. But nevertheless, as mentioned, I joined faculty last year in April, and I'm building right now a group. There's also a bit of advertisement there. So I'm working right now at the Nürnberg Institute of Technology. Well, it's known for the fact that Georg Simon Ohm, the father or like the inventor of the namer of the electrical resistance comes from, and this is also the university logo with the omega sign. But now coming to the lab, so I'm actually interested in having or building systems with a really strong focus on real applications using neuromorphic system and neural computing in general. You can just try to scan the lab website if you want to have more details. But like basically what I'm working on right now is putting together an agenda on processing intelligence and control using efficient compute systems. Because, well, I have some experience with neuromorphic computing back in the days where Spinnaker was still trendy and the silicon retinas were still like custom boards developed in Munich and then in KTH. Well, my focus was in interactive closed-loop systems. So this is why I will look at robotic applications, but I'm also spending my time in learning algorithms design and so on. But again, the topmost part of the pyramid, we have the fast, efficient, and robust and green inference. Well, as I mentioned, I will talk about the project which I developed together with some undergrads, but at the moment, let's put it this way, this is the lab. So we started in April last year. We didn't have too much time to grow, but like at least we have a bunch of hard workers. The heavy lifters are Ertan, Julian, and David, and this is myself making actually more or less designing logos and algorithms, and they do the heavy lifting. But other than that, I'm actually hiring. So I'm hiring people out there having really interesting masters, or like interested master students, and or talented people looking into applying neuromorphic systems. So again, disclaimer: we don't design, we just do applications. So we have a bunch of people with control engineering experience, with data processing, with big data, and we come together and try to build a group which is focused on applications. And for today, I prepare for you a short overview of the solution, our award-winning solution for the Vision Zero San Jose Challenge, actually the TinyML Challenge, where we had Sunny and BrainChip and Infineon as sponsors. So they tried to like support teams from companies and universities to come up with a solution for the detection and tracking of pedestrians on roadside. Of course, well, I'll just try right now to like give you a brief introduction on the goal of the challenge, our solution, a bit about the sensing and the algorithmics that we actually put in, which is the big neuromorphic part, and then a bit of performance evaluation, deployment analysis, because we're tasked to have a deployment ready solution. So we'll actually introduce an end-to-end application development process. At the end, I even have a bill of materials because we also had the task to come up with an efficient, budget acceptable solution. So Vision Zero is a street safety policy that strives for the elimination of traffic fatalities. Basically, the task for the challenge, for the TinyML challenge, was to design a cost-effective and accurate solution to detect pedestrians during day and night in order to implement safety measures. Basically, the solution should have a very good energy footprint, should be robust to day and night changes and weather changes, and should come with a budget that will allow scaling to a city level. Well, without further ado, I will introduce the solution because you are interested in the details and how we actually put up an end-to-end pipeline. So basically, thanks to BrainChip for supporting us with an embedded development platform, and the Neurocomputing System Lab at KTH Stockholm for the camera, for the DVS camera, is basically a custom DVS event-based camera developed back then in my time at TU Munich together with your Conrad, and actually got one of these. Of course, we actually see a huge bottleneck of the system already, this huge well, not like 1.5 meter long USB cable, but we'll come in a second to that point. But the solution, the hybrid solution, so to say, actually got data from the sensing part, which is a DVS, an event-based camera, and send the events in two separate parallel pipelines. One was designed for the detection. Basically, we had a spiky neural network used to detect pedestrians in the scene based on event data. And the other parallel pipeline looked at tracking. And it was an event-based expectation maximization algorithm. So basically, we took an NEM algorithm and we made it event-based for our task. Yeah. Interesting is that we actually were able to have everything running on the embedded platform, but I'll guide you a bit through also to the solution life cycle. So we started with the data acquisition module. So basically we have the DVS camera. What you see here is a custom module with a DVS sensor, the same that you have right now in the innovation cameras. And back then we designed a board with a standalone microcontroller, back then a 32-bit ARM core, which actually got all the events out of the DVS and spit it out on the USB. Then we have the two parts. One is the deployment of the event-based expectation maximization for tracking. And on the other side, we have the spiky neural network for detection. So one is the detection of the classification, and the other one is the tracking. So we had the two sides of the deployment. And actually, right now, what happens is that we had this nice setup with the BrainChip, which runs on a Raspberry Pi carrier, and the BrainChip is just a board which runs on a PCI port. And the whole idea was to leverage this hardware in order to get a cost-effective, low energy footprint solution for the pedestrian detection. What you have here, we've chosen to go for a completely open. So whatever you see today is open source. Yeah. So for the part with the spiky neural network, we actually decided to go for something which is a la hackathon style, hence not developing everything from scratch. So we looked at Edge Impulse, again, one of the sponsors, and they had really nice ways of designing or like building system with the Raspberry, with the Akida brain chip target. So what we've done, basically, we went in their online cloud API and we built a pipeline for spiky neural network based detection. For the as details right now, basically the neural network that we used and designed in Edge Impulse is MobileNet V2, is a fast objects, more objects like MobileNet version. We actually cut off the last layers of the MobileNet and replaced it with a per region class probability map. Basically built heat maps or where our looked for objects are, and we actually use that in our deployment. Yeah? So in short, MetaTF Akida, fast objects, more objects based on event-based data. Now we have to be clear. This system didn't get pure events as input. Actually, we aggregated the events because, well, hackathon style, we didn't have time to design an interface to ingest raw events from the camera in Edge Impulse. And we didn't even have a professional license, but we actually had enough to build the spiky neural network and design it and tune it online and then actually download it and flash it on our brain chip Akida. Now, if you want to have a look at the project, you can actually scan the QR code there and you'll go directly to the Edge Impulse project. You can clone it and play with it. Actually, they offer around 30 or 40 minutes of free training on their server to actually be able to test your model and actually evaluate the first level of performance. When you look at the sensing, I actually put that as a life cycle part. Basically, we made it a bit didactic. But when you look at the sensing, I wanted to come back to the fact that we got the custom DVS camera, again, to TU Munich, KTH, and we collected data in Nuremberg. So we went and mounted our pole in urban intersections or a wide urban road street and even at night in Munich. And we collected camera data as ground truth and event-based data with our camera. And the interesting part is that we also actually release the data sets. I'll show you, I'll post in a second a QR code. You can actually go in Zenodo and find the data sets. But the main idea is that we had this kind of parallel input. So we have the ground truth normal camera, and then we had our event-based coded with green. We had the on events, and with red we have the off events, just for those who already work with the DVS camera to know the conversion in our system. And the task was to actually detect pedestrians which perform a normal motions roadside. End of the day, we ended up detecting pedestrians roadside, and that was it. Yeah. So being able to distinguish between pedestrians, bicyclists, and cars. Now coming back to the model, the algorithmics, I mentioned earlier that we looked at a spiky neural network implementation. So it's basically a spiky neural network is a quantized model, a fast object, more objects, a ConvNet, a MobileNet V2. Again, the only special thing is that we added a custom loss function, which forces the network to fully preserve the locality in the final layer, so the locality of the data in this heat map. And what's important also to mention is that we embedded a physics model of the pedestrians. So we embedded a skeleton. And now, for the sake of clarity, each of the events or events coming from the camera were actually matched to the three segments we defined: the arms, the trunk, and the lower body. We'll see more about this in a second when we talk about the tracking. But at the moment, the heat maps were really useful in the MobileNet model, just to make sure we are able to to just cut the end of the network and actually have this beautiful per region class probability map at the output. The thing is, the FOMO doesn't have object, like other object detection algorithm doesn't have outputs bounded boxes. So we don't have bounded box outputs. Yeah. So basically, what we've done, we had these heat maps, these probability maps, and then of course it's easy to go to a bounding box. But like we just had the bounding box just drew around based on these heat maps as a visualization for us. Now you see the system at work. Actually, this is running with a Flask server on the brain chip board. Remember, the brain chip board lives on a Raspberry Pi carrier. And what you see here is actually the tracking performance for the pedestrians. Of course, not perfect, but you see the two dots depicting the two dots where you have the upper body and the lower body. Yeah, don't expect 100% accuracy and so on. Just expect a hackathon done by undergrads, so fourth semester students. I was pretty impressed about their dedication. So here we are. We had a system which actually scored pretty well, and we had a system which developed, which actually took advantage of the spiking or the neuromorphic hardware. When I look at the other side, where the actual, I would say, innovation of this project comes out, is basically the pure event-based expectation maximization. So we embedded the skeleton kinematics inside the system, and we looked at extending expectation maximization with the prediction model. And what we've done, we took events and tried to match them to one of the body parts. So what you've done, you actually have maximizing the likelihood that one event belongs to one body part. Of course, if you want more details, I can give more details about the actual steps of the event-based expectation maximization. Basically, there's a ridge regression. Then we have like some moving average because this works in real time. So each event has a contribution in the estimate. And basically what we've done, we combine all the estimate based on angle, on the body segment angle with respect to the others. And then what we've done, we have like a merging part where we actually combine all these estimates and computed the membership to our body segments. And basically the likelihood was the sum of all these contributions. Yeah. So we had this like body segment in the lower part where we actually then matched all these events. So in one word, this was the innovative part of the project where we actually implemented a tracking algorithm based on raw events from the DVS camera, and we fed it in expectation maximization. It's basically, for those interested, like 500 lines of C code running directly on the embedded board. Important to mention, the spiky neural network actually worked on the neuromorphic, the brain chip Akita, whereas this expectation maximization worked on the Raspberry Pi. So it's completely hybrid solution because, well, given the time we had, we didn't really have time to explore how to put the EM on the brain chip, and the Meta TF didn't help us too much. So we are in the stage in which right now we're further developing the system, but just keep in mind, Spike neural network worked on the Akita for detection, and then the expectation maximization, event-based expectation maximization ran on the Raspberry Pi. Then, if you look at a short demo, we have the events coming from the camera. Here is a small piece of code we developed together with the students. And we have, on the left side, we have the events coming from the camera. You have the ground truth in the background. And basically, the tracker visualizer, you'll see here coded in blue, yellow, and red, the body part segment, and the event membership likelihood computation. So the fact that you have colors on the events actually reflects the fact that they belong to a certain body part that we embedded in the physics, in the kinematics of the pedestrians, or of the bikers. Now, if you look a bit at the performance, again, don't expect NIPS-ready performance tables, but we actually did it pretty nice and systematic. So for the qualitative evaluation, you have here a glimpse in detecting pedestrian and bicyclists. So this is the detection. This is the part done by the spiking neural network. Whereas in the tracking, we'll look at expectation maximization. So basically, we perform multiple experiments, and then we did it a la textbook. We took data, we perform a number of experiments, we did some statistical tests so that we have some really nice quantitative evaluation on the table on the right side. And we took the basic metrics we could get. So we had like the confusion matrix and an F1 score, which actually kind of give us an intuition of how good our detection was. Again, limited for the fact that we didn't have too much training time available in the platform. But again, it was an experiment for us to see if we can get something really nice, even with the limitation, so to say. On the side of the event-based expectation maximization, what we see here in the qualitative evaluation, again, what we have here is the bicyclist tracking. Again, events, the green events are the on events, red events, off events in the upper part, and the lower part, basically you see the coloring of the body segments. And again, to remind you, we separated or embedded the body structure in the algorithm, and then through expectation maximization, we actually maximize the likelihood that one event belongs to one of the body parts. And we found, of course, some metrics for the quantitative evaluation, which found actually relevant for tracking. And again, we did the same batch of statistical significance analysis, as you see it here on the left side, but we put out some numbers just to demonstrate that we had a reasonable detection rate for the bicyclists and the pedestrians, and the rest was just background. Again, I have also more details on this metrics. I had to actually put it in an article we wrote lately about us, and I can give you more details. But basically, we're pretty happy with the performance and the fact that everything ran on the embedded platform. And now, what we're actually pretty happy with, of course, in the performance, in the model choice, and parameter tuning, we can spend days and nights and make it NIPS ready. But like NeurOMorphic, sorry for the new name. But like for us, it was important that we have also deployment. So here we are, the deployment. Basically, we had a system which should run out there and should take as little energy as possible and should detect and track pedestrians roadside. So San Jose mayor actually said that also, because he was the one awarding the prize at the end, actually said like, yeah, we're actually trying to minimize the energy footprint of our infrastructure. So here we are, we actually appeal to TinyML and the industry to come up with such a challenge to see what kind of solution can we get. And this is why I also have a bill of material at the end. But basically what we've done, we were able to also measure the power the system actually got, and I'll give it for you here in the right-hand side table. You have it for the 3 data sets. But basically what we've done, instead of having the measurements outside on a gantry, we actually put a screen in front of the DVS camera, and like it was a huge screen, so we're able to actually replicate the scenario outside. Of course, with the lab lights, yeah, one can argue dynamic range of the DVS is good, but you just demonstrate the lab conditions. Sorry, one can go beyond, but like, okay, good luck measuring power with a mobile setup outside on the gantry, which is 8 meters on top of the street. Aside that, basically what we've done afterwards, we also wanted to see the weatherization capabilities. So we took the board, the brain chip board, and the DVS inside an oven, because they said, okay, your system should also survive and did not have a huge performance deterioration when it runs in California sun, when you have 65 degrees Celsius or even more. So, okay, we take our system, we put it in the oven, we put it at 65, and of course we cannot put any screen there and measure like or detect pedestrians, but we actually pointed at the fan, and the cool part is that we are actually able to generate enough events to have passed through the algorithms. So at least they generate something. I cannot talk about performance of the algorithm, but the algorithms, both of the spiking neural network-based detection and expectation maximization-based tracking, were fed with events, so that the algorithms were actually running and drawing a lot of power. But basically, the power they drew was not that high, and we actually measured something which was around, like, let's put it this way, average like 6 watts, and this is wall power. So we measure the power consumed by the entire Raspberry Pi carrier and the brain chip Akita. Yeah. So actually, the power drawn by the current drawn by the whole board. Yeah. And we see on the 3 data sets, performance is kind of different. And like, I didn't put right now here the numbers with the oven because there was insignificant differences. So basically, we also demonstrated the weatherization capabilities of our system. And for the complete bill of materials, because we're also like challenged to do that, we actually came up with 2 solutions. One, again, this was for the hackathon. I actually checked the Samsung Smart Things. I think this is not available anymore. So unfortunately, we cannot buy the 70 euros DVS cameras anymore. And alternatively, where we had the innovation-based sensor, okay, you can get prophecy if you want HD and so on. But basically, they were actually pretty happy to see the fact that we had the best price of around $200 for the cheap low-res sensor, and we had like around $3K for a full-blown HD version. If we went for the innovation or the other sensor out on the market, yeah. And because the brain chip kit is pretty cheap, yeah, so we actually round up if we want to scale up to the city level to a really nice solution. They love that. They actually love that. And now, like, if we go on, I also want to like say that we actually put something out there. So we had some data sets. So if you scan the QR code, it just like you get around like 3 data sets with DVS data and movies. My students uploaded it, so you can just get it on Zenodo. Then we have the code release. You can actually check both the life cycle model where the spike neural network is and the TinyML, or like the expectation maximization. Sorry guys, I just saw right now the question on in the comments. So I was in the private chat. Sorry guys. I will just take it at the end. And then for the solution release, what I put there in this slide, if you scan it, that's actually like a YouTube movie guiding you step by step on actually kind of trying to run the code on the brain chip Akita and actually look at the code, which is there right now in the GitHub. So you can check it out yourself. So both the expectation maximization and the spike neural network model. So I give some like some minutes right now if we wanna scan it. Otherwise, I think this talk will anyway be online, so you can scan it yourself. Yeah, so it's everything open source. So no strings attached, nothing hidden. So I will like try right now to wrap up because I'm pretty advanced right now in the talk. So as you see, I was pretty shallow in the details, but again, we can go on in details in the eventual question rise up. But I wanted to show you an end-to-end solution. An end-to-end solution which actually got pretty good feedback in the hackathon. And basically, we proposed a low-power neuromorphic sensing and processing platform. Yeah, so we had like the brain chip Akita on a Raspberry Pi carrier. We had the DVS event-based cameras, and we had only local processing. This was beautiful, and they loved that as well. And we provide good accuracy. So I'm not using any superlatives here. Good accuracy for robust visual detection. We tried also in dark or like in a sunset, and we were like pretty there with like the same values with the performance. What are we actually now working on, because we got really good feedback also locally in Germany, we actually port the system away from the custom old DVS sensor we had, which was fantastic to get us started, to a Prophecy EVK3. So we go to HD now. Then we look at new computing platforms. I know Simsense spec has also like 128 by 128 pixel. So we can't do too much with that, but like we really hope that Dylan and the folks and Sadiq will work on and bringing this on. And let's see, because right now we still, like for the scenario we had at hand, which I've shown you here, we had the pole with the sensor mounted 3 meters above the intersection, and we had the 128 times 128. So the smallest resolution DVS we had available back then. And the cool part is we're actually preparing this noise development for a city scale development. So we have right now authorization to mount such systems. So we try to multiply as well in a town south of Nuremberg. So we got right now also the authorization to mount this on the gantry in the city. And the cool part is that in Germany, we still have like really strong rules on privacy preserving, and DVS cameras are ideal for that. So private sphere or privacy preserving cameras are really strong argument that also made up like close to having such a nice opening to adopt such a system for a real world system. And now to wrap up, guys, dear neuromorphic community, today I wanted to bring you like an end-to-end application development scenario in which we use event-based cameras and together with some nice neuromorphic hardware. Again, I know there are discussions, which is the low power platform out there, which is not, and so on. BrainChip might not be the best and the low power platform, but again, for the hackathon, for us was really interesting to explore, and for me to come back in the community with a really nice tour de force to ramp up on algorithms and so on. And I'm so looking forward for your questions. Thank you so much, Jens, for the invitation, and Gregor and everyone from Open Neuromorphic. Happy to be here.
Thank you very much for a wonderful talk, Christian. I really appreciate your approach. Like you're excellent in finding wonderful ideas and executing on them to get very tangible results. Like I don't know if it's obvious for the audience, but I think stitching all this together is a tremendous amount of work. So thank you very much for talking. There are a few questions I'd like to highlight from the audience, and specifically talked about this very interesting platform called Akida from BrainChip, and Gregor is asking, like, I think in the talk you made it clear it's deployed by Akida, so you actually run these things on the Akida chips. But are you then training conventional like non-spiking and then converting in after training?
So the whole thing was again, like I went off spiking for a while. So for me, when I came back, Edge Impulse was one. Like it's a company, they develop like in the cloud, in the browser IDs to develop like to design system like that. It's like, okay, well, I'll give it a try. I spent like, I don't know, 1.5 hours, and I got a system running, which I was able to download and put on the BrainChip Akira. So
you could,
guys,
in 1.5 hours, you converted a network into spiking and ran it.
I got the FOMO, which they have in the libraries. They had also, like, together with BrainChip, developed the meta TF conversion level where they quantize the network, which is designed in the Edge Impulse, and they actually you download an MBZ image, you put on your BrainChip, and it runs.
That's so fantastic.
I'm not paid by Edge Impulse or something, but like for me, coming back and finding such new amazing tools with such a plethora of embedded targets to develop edge intelligence, thumbs up. Really good job.
That makes it very usable, right? So you don't spend months to set things up. And Greg is also asking, so do you know what the power consumption for each of the different boards? Like, so I guess Raspberry Pi is a couple of watts, right? Do you know how much the Akida chip uses?
I couldn't get more than the actual. You saw it in the slide. I'll just try to put the slides back up. When I actually ran the demo, I'll just a sec. Give me a sec. I'll put the slides up if I'm able, or just a sec. Yeah, I'll put the slides up, because what I could calculate without actually putting wires on the BrainChip Akida, which is anyway on a PCI. Yeah. So yeah. Anyway, I'm an electrical engineer in a computer science department. My students don't know so much about this kind of stuff. Yeah. So I actually asked them to look at what can they do and compute it on board, and BrainChip Akida actually exposed an API to do that, and I'll show you in a sec. So what we actually had, we had this. So guys, you see my slides. You see the power consumption per inference step. Yeah. So this was actually calculated on the BrainChip Akita board. So
Okay, so
this
without the Raspberry Pi platform.
without the Raspberry Pi. So more like info or like more sensing data or like current values or what values I don't have from the BrainChip only. I gave you the world power for the whole system because this was important for us in the hackathon to sell how much it draws. Like 7 watt, man, it's fine. Whereas the BrainChip, I think they did their own measurements, and what we've done with the API they exposed is like around 6 milliwatt per inference step. Yeah,
that's
and you see the inference speed is around like a quarter of a second.
Yes.
Yeah.
Well,
I mean, let's say 100 of a second.
Exactly. But that would be inference speed for one single frame then.
For one frame, yeah.
Yeah, and that then speaks to another question also from Gregor. Thanks for all the questions, Gregor. But do you then send in frames one by one? Okay. So that's a dense representation, or do they have like a sparse coordinate representation?
It's just like dense, like it's like matrix. Dense representation matrix of events, but aggregated as mentioned. Yeah, we couldn't figure out how to ingest in edge impulse raw events. One can do it, but needs additional effort, and we didn't want to put it inside.
No. I mean, this sounds like if you can get this running in 1.5 hours, then it's just a matter of finding the right model. This is very impressive.
The 1.5 hours was the edge impulse. This like building the model and configure it a bit in the web, and then downloaded the target for a BrainChip. What you see here in this slide, it's a Flask server running on the Raspberry Pi, then getting data from the BrainChip Akita, making this nice window, showing where the track points are. So there's a lot of boilerplate around. This I didn't do in 1.5 hours, but like a bit longer with the students together.
But with that technology stack, I'm still impressed you get that number of power consumption at the moment. That's fantastic.
Well, again, with a grain of salt, I am using a BrainChip API. So yeah, I didn't measure.
Of course.
When I put the measurement for the wall power for the whole platform, I put the cables and I measure with my own devices. But here, how these values come up from their API, I will just say check the code.
But at least for the whole system, if you just look at that, right, there's still orders of magnitude better than TPU platforms, right? Which would be another way to
look at this. Yes. Yeah.
So there's another question relating to the work you've done on the spiking networks and the event-based cameras. Can you say that spiking networks only work with event-based cameras? Another way to frame that question.
No.
Yeah, right. I mean, but what's your experience like? So couldn't you solve it with something else? We can maybe talk about that. Right?
Of course. But
what's the benefit?
What's the benefit? Because like the benefit I envisioned is actually making these networks run natively on a platform which consumes little. Full stop.
There's no benefit in accuracy or precision. It's literally the energy argument.
So at the point, at the level of depth we spent on improving the spiking net itself to match the hardware and to be optimized to the point of exploiting fantastically the BrainChip Akita platform, I would say it's just the power consumption. But if we look at really also exploiting other advantages from the accuracy point of view, indeed, one spends more time in making this network, in tuning this network, which also one can do in Edge Impulse, actually getting into the code and tuning the network itself. Also in the quantization library from MetaTF, from BrainChip, you can go even there and even like tweak more the parameters and actually also take the accuracy to a different level. We took the, I would say, out of the box-ish implementation, not the one which we could have improved. Definitely more place for us in current development, but I would say at the moment we chose this setup or this constellation, this recipe for the power consumption.
Fantastic. Yeah, I think it's a wonderful demonstration again, and again, the energy argument is very strong. There just came another question from Gregor actually. If a synchronous edge chip that exploits sparsity like Akita burns just 5 milliwatts, is there a point of event-based asynchronous systems? Like, could you argue that do we even need event-based asynchronous system if this thing is so good?
Yeah, because we have a digital chip here. We have a synchronous chip. Yeah.
But is it asynchronous, Akida?
Is it? I don't know. I have to check it out, but I think it's.
Maybe someone in the chat can help us here. But I mean, would you say that's even a need for?
It's asynchronous, but it's digital. Yeah, so it's fully digital.
So would you say there's even a place for? Let's say we talk about neuromorphic devices that are then mixed signals, right? I mean, they come much close? Don't they come much closer to this as well? Like, I mean, is there a reason for going there even?
It will be a reason to go there when you want when your data is actually so sparse, generated, like your sensing data is so sparse, and you want to process it natively with a really low power budget. But as I see it, we might have to face a situation we have commodity hardware and not always mixed signal neuromorphic devices or analog devices. So we might still live in the digital world, and there we have to pay the price of switching of transistors. So basically, you have to pay the price of higher number of watts. But one can go there as well. Actually, we look at the spec from SynSense, because there you have like monolithic processing. So you have the chip behind the sensing. So you ingest directly the sparse events from the camera directly in the processing neural network behind. So I don't know. I would just say it might be a point of using a synchronous system, but as I see it, with the current development of application side infrastructures for the police, they still want to mount a camera next to the sensor to have ground truth and semantics of the scene, not only the event-based fast detection, sparse, fast reaction to the scene changes. So if I will come up with a really fancy mixed signal or just analog processor for the events, I don't know if they'll be so excited, because they'll ask, okay, how do I read out things of this? So you still need the digital part there. So
I mean, that's the problem with analog systems, right? They are then the physics do the compute. There's no readout like such. But I mean, it also, I mean, it would be interesting to understand how this relates to other different neuromorphic platforms, like you mentioned the spec chip from the SynSense company, right? But again, I guess it will also take additional effort, because you'd have to take your model and translate that into their ecosystem and see how it works, right?
So, and now, like coming back to ecosystems, because I know where we are, and I remember how we worked back in the 2011, 2012 in the neuromorphic community. Like there was custom software for every piece of hardware we had. So we had like libraries written by everyone in small, like C++, was Python, whatever. Now initiatives like Edge Impulse, or like I see also SynSense, like they bring nice, really nice libraries. Also your efforts, Jens, with your address event libraries and the NIR. I like this. I like that we have more mature, more like broader libraries to program such devices. But for the end user, for the people which are not neuromorphic nerds and geeks, we need something which is tangible and easy to use. Otherwise, now I like even introducing my students which are nerds, they're like still like, okay, I show them right now like with a spec. Rockpool is nice. Synapse is nice. But like they still have difficulties.
It's a huge problem with the walled gardens. Like each system can be very, very nice, but you still have to relearn it if you jump to a different chip, right? But I also said this before, but what I really like about your research is that you kind of circumvent that problem. Like technically, your networks are neuromorphic, they're spiking. Right now, they're running on the Akida chip, and you can argue maybe there are different ways of going about neuromorphic, but at least you show some results.
My point is that also, like for the community itself, guys, we need to show tangible results in real world problems. No more toy scenarios. So like literally, like I like together with the students, we hacked something. This doesn't really qualify as fantastic contribution in the neuromorphic community. Maybe the event-based expectation maximization, because that's a really neat thing. But the rest, I would not say that this will become like a best paper award in our community or in a conference of ours. No, but people loved it because I shown them values of watts which they like. I showed them something which is embedded, and they didn't really care about the spiking nature of the system. They care about, like, man, it uses little power and it's there, and it can have a really broad dynamic range, day and night detection, and we get around 90%-ish, 80%-ish accuracy. So what do you want more? People need this kind of input. Yeah.
So basically, you're coming on the other side of the hype cycle and actually delivering results for the neuromorphic platforms, right?
Not groundbreaking, delivering something which can be used and can be now, as I mentioned, we go there and we go to Stadt Schwabach, we go to Schwabach city, and we'll mount this on the streets. Not with the 128 20-year-old sensor, but with the Prophecy EVK, yeah? And Prophecy offers now a really nice library, so we'll basically try to build around that and integrate a system that we developed or updated to the next level. Yeah. Again, I advertised a bit many companies and many universities, but I think it's also for us in the community good to know who's who. Yeah.
Oh, exactly. And there's just a comment that says that the use cases for this is huge, right? The number of things you can solve with these technologies is wonderful. But actually, I actually like to take it half a step back, right? Because now I think you have hard-hitting arguments for event cameras. I mean, you talked about dynamic range, response time, and so on and so forth, and for the use of at least partial neuromorphic digital technologies, right? Those are excellent arguments, and as we talked about, now you can actually apply them and people are interested. Another concept that we talked about briefly in the beginning of the talk, and that you at least got me smitten with, so that I really I enjoyed learning about, and I've been researching ever since, has been this idea of anti-fragility. So my question basically goes, now we've talked about these very wonderful but feed-forward systems, right? The fact that you can take some signal and do some classification or recognition based on it. Could you maybe pull us over in the control sense or in the anti-fragility sense? Do you see this work relating somehow? Is there a connection?
Well, yes, because as you look even on the current slide, yeah, we had like robust visual detection. Think about it. I worked also in my time at Huawei, I worked a lot in traffic control. So basically closing the loop with traffic data, which back then we got from induction loops or cameras. Yeah, so basically sensors to count the number of cars passing. If you look at the system I presented, you can ignore the pedestrians actually and just count how many cars you actually see in the scene. It's even easier than a normal camera because you have only the events and you can detect the cars and count them. And yes, we could bring such a system that I presented today as a feedback in a traffic control system. Basically, you use the number of cars passing in a certain crossroad, right, intersection, and then you can adjust the traffic lights based on that. More cars, more green light, less car makes no sense to have green light because then you have upstream or downstream accumulation of cars. So basically, you want to aim at green wave. Yeah? I will have actually another talk if you want to talk about this. But interesting, if you want to look at using such a system, which is robust because it covers a really wide range of context and conditions for the sensing environment, I would say we could aim at having an anti-fragile control system. What is anti-fragility? Again, I'm advertising a bit. Together with researchers in multiple fields and many other universities, we build right now an anti-fragility control or an anti-fragility system group. Basically, we look at how we can redesign systems which are beyond robust. So systems which can not only just resist, I would say resilient system, or just robust to absorb changes in the parameters of their operation or the perturbations, but also gain from it. And of course, the first intuition you get, okay, where you can gain. You can only gain if you have a closed loop, because if you don't have a closed loop, you cannot gain, because you cannot use the sensed information back into your algorithm to actually push the system to a point where you can gain. So to answer Jens' question, yes, we could use such a system as a feedback loop for a traffic control system which might exhibit or which would exhibit anti-fragile behavior. Yeah.
So so you would consider this to be like a precursor, like it's a signal processor basically that can feed into your controller.
Yeah. Basically, it's the feedback loop. Yeah. So if we take the control theory a la undergrad, wait a second, I lost you here. We could say that. Wait a sec. I will put up. Can you see the new? Oh, wait a second. I'm sharing the slide. I'll just change the share. Because we're talking now, and I wanted to actually make sure people also follow it. So if you just Google antifragility science, we have this new website here. I will not spend too much time on where it comes from. Of course, it comes from the book of Nassim Taleb. But the cool part is we actually gathered a bunch of people from different domains and different universities, which we are interested right now to build systems which are beyond robust. And now, because I have the chance to talk also about it in the neuromorphic community, why not building neural computing systems which are beyond robust? Yeah, we can go a la dynamical system, we can do analysis, and we can show that such systems, neural systems, together with the native execution of neuromorphic hardware, can actually make systems like traffic control systems beyond robust, basically to gain from uncertainty and perturbations. And as you see here, we have a bunch of people from all over the world, people doing, like myself, applications of neuromorphic and low power AI. We had people working on traffic robustness, people working on ecology, people working in traffic control, people working on robotics, people working in control systems, and people working in cancer as well, cancer therapy design. Yeah. So as you see, we're a multidisciplinary team, but we all speak dynamical systems. And
but it's also my understanding, like if you want this kind of feedback, right, you have to have some kind of update mechanism, right? Wouldn't you then need a different platform? I mean, would this work on an Akita chip, basically?
I would go back one step and say, yes, I would try to use it on a computational substrate which exhibits such features. Neural networks, or I would say spiking neural networks, are dynamical systems as such. I'll use them as a substrate, and then, of course, when it comes to execution and pragmatic aspects, I will use then neuromorphic hardware to actually natively execute them. But my current investigation goes along the lines of anti-fragile control in neural networks.
Okay, so really taking the concept from literature and pulling it into neural systems.
I take the concepts so what you see now also on the website, this is traditional, I would say, research where we actually have multiple parts to induce antifragility. So we look at mathematical modeling, control systems. But now I take one step further and say, I want to implement such algorithms in a substrate which inherently has robustness, resilience, and why not, hopefully, antifragility, which are neural networks.
Okay, so this is very interesting. There's a question from the audience that talks about radars. Maybe let me extend that to LiDAR data as well. But both of these technologies are a huge trend, especially in the automotive industries. Do you think that that can be combined with this neuromorphic architecture? So I guess both for the inference, maybe also control setting.
I would go one step and say this is all about sensor fusion. Basically, we have this sparse representation which has temporal dimension embedded, which are the event-based cameras outputs. And there's this radar and LiDAR, which also offer like this kind of sparse representation of like point clouds from the environment. My initial thought will be sensor fusion. We actually done work back in the work time at TU Munich where we actually fused depth sensors with event-based cameras, where you actually augment each event from a DVS camera with the depth information. Yeah, so you fuse event-based with the Kinect sensor. It provides depth, so you can get
essentially like a three-dimensional signal.
You can get a three-dimensional. Then events, of course, two-dimensional. Events are also three-dimension, a four-dimension event.
With the polarity, you mean as a third dimension?
With the polarity as well, and basically the depth. So I would say yes, automotive is the way to go, because of course we can also benefit from the fact that we have embedded platforms which take less power, but also from the fact that the representations are more efficient, so to say, and they can be easily combined, a la time or a la space. Space and time.
And I guess the method you've applied here, which is to build up the network and maybe take inspiration from existing architecture outside of spiking, can still apply to bring that into the spiking domain via this SNN conversion.
Yes. Yes.
So it'll be the same method.
I would say, because like, again, I'm also teaching neuromorphic system, like neuromorphic computing and system in Nuremberg. And the cool part is that I also try to put on the intuition that we talk about dynamical systems. And then this gives us so much flexibility and versatility to implement certain dynamics, but it's up to us to craft such system.
Yeah, so to be specific, you mean that instead this is like counter to the digital instruction set, which is very discrete, right? You can actually model the dynamics in the neuromorphics to fit some dynamics in the real world, for instance, right?
Yeah. And then, because neuromorphic, like neural networks, spiking neural networks offer the language. We just talk in dynamical system. I actually read your preprint on NIR some days ago, and I find it's perfectly matching as a unifying concept. So we talk dynamical system. We use neurons because we have interesting processes that we can embed inside, like circuitry, like winner-take-all functionality, competition, cooperation, adaptation, learning, and then having a neuromorphic platform which runs that natively. What do you want more? So we model problems in dynamical system. We implement that in neurons. We don't have yet a unified translator from one to the other, but we work on that with NIR one step further. And then we have already many platforms that if we could do that, we can actually get dynamical system in the real world and actually implement them efficiently on neuromorphic hardware.
That sounds amazing, Christian. Just before I have a final question for you, there's another question from the audience. So neuromorphic architectures can have better results than neural ODEs to model dynamics. Is that the case? Can we get better results using neuromorphic systems than using? Yeah.
That's a really interesting problem. It's actually a question, and it's actually related to a previous work of mine, where we actually looked at control of traffic control. And then we have two choices, because we model the problem as, okay, it's a longer story. It's another lecture, but we model the system as a dynamical system. We know that traffic lights are periodic. Green light comes every number of seconds, and you have a maximum of 120 seconds in an intersection of cycle time. So it will repeat at maximum 120 seconds. So basically the sum of the times you allocate to each direction in a crossroad, it's 120 seconds. Good. You can model this periodic system with an oscillator. Whoa, bingo! Oscillators are well studied, well defined in neurons. So what we've done back then, this was an ECML 2019 paper. What we've done back then, we just took the model of the dynamics and the data we have from streets, recordings of cars passing and traffic flows, and green time allocations, and we trained a system using oscillators, implementing spiking neural networks. Back then, not on a neuromorphic platform, but on a huge cluster using open MP, and here we are. It was basically an ENGO model. It was an ENGO model running with the OpenMP background, and it was OpenMP and OpenCL. It was also a bit of GPU acceleration, but it was an ENGO model. So here we are. Model the problem, and then the oscillators are ordinary differential equations with three terms, where you actually bring space and time and the architecture of the street network of your city and so on.
So is it fair to say basically that it's not necessarily better results than if you would model an ODE differently, but kind of the substrate is very closely linked to that formalism? Like, so let's say we could get an analog system, right? So find some kind of a physics based, that then the implementation of that would actually be that dynamic the very same.
Yeah, yeah. That was so actually in this case we went beyond and we actually got even better performance than actually integrating the ODEs, because for integrating ODEs you have methods like Newton-Raphson, Runge-Kutta, and so on, and with the internal decoder solving of Nengo we're a bit faster.
Yeah, so the point is, with all these methods you get like numerical imprecision, like it's imprecise,
well.
you get errors. Yeah.
And we used it to our
amazing.
advantage in Nengo, yeah.
Yeah. I can't help but point out one paper which I'm so fascinated by, because what you talk about there was actually already published in a paper called the simple neuron servo mechanism from 1991, where Carver Mead and Carl Ostrom, so the Swedish control theorists, famous for his adaptive control, talked about exactly what you're saying, that you can actually model these kind of oscillators, for instance, really precisely with just a very few neural primitives. If you're interested, so from 1991.
I will check it. I think we can even find this paper right now we're talking about. Yeah, look at it. We actually. Yeah, we found it.
We should put these references on the chat page so people can
I'll put it on. I'll put it in. So like join the chat and just I'll connect to YouTube to connect. Okay, wherever. Wait a second.
I can also upload them afterwards on the talk page.
Yeah, well,
I have one final question for you. Now we talked about a lot of different topics, and you've obviously been around. I mean, you have a ton of experience here.
Yeah.
So, what do you think is the future? Now we talked a bit about the control and the feed forward, right? What's the next step? What should the community be focusing on? What would be the advice you would give to young hopeful PhD students or master students?
So aside the young hopeful PhD students which don't work on hardware and developing and improving the neuromorphic hardware, because I'm talking from the side of not being the one designing chips and so on, I would say grab on applications and do impactful demos. That's it. Grab
an application and solve problems.
Yeah.
Do an impactful
and demonstrate that the chips, that SimSense, that Prophecy, that innovation, that ETH teams, that everyone is like building in all the labs doing hardware worth. So
wonderful,
guys, happy to receive hardware from the teams developing. Happy to put them in applications, especially in the point of applications where we have dynamics in the real world, whatever that is, floor shop factory industry, traffic control, whatever. And I'll be more than happy to design systems and then to the point of having you as a collaborator to actually run them natively on your amazing new developed IP core.
Absolutely fantastic. With that, Christian, I'd like to close. Thank you very much for your time. It's been an absolute pleasure. And I'll just have to advertise for one more thing, which is that, of course, these talks are continuing. So please don't forget to share, like, subscribe to the Open Neuromorphic channel. We'll continue on January the 25th with a talk on exactly a platform called the IBM North Pole by Carlos Ortega Otero, if I pronounce that correctly. And then again on February the 5th on a unified instruction set for brain-inspired computing that Christian was also mentioning a few times here. So thank you very much for listening in, and we hope to see you next time.